I'm going to take a minute to introduce our presenter for this evening. A few years ago, I got my amateur radio license, my tech license. And with all the levels of license that I achieved, I took a class and it came with a manual. And so I brought those manuals here with me tonight. This is my ARRL ham radio license manual. And when I open the manual up to the front page, what do you know? It says written by Ward Silver. So a couple of years later, I moved up to general class. I opened this manual up, see who wrote it. Once again, Ward Silver. About a year later, I worked up to my extra class license, and sure enough, we opened it up to the first page, and the book, the extra class license manual for ham radio, was written by Ward Silver. So I thought, well, let's just keep going. So I happened to purchase this ARRL operating manual, and I opened it up, and there's about 5 different people that edited this book, and none of them was Ward Silver. And I was a little surprised. I said, how about that? So I thumbed a couple of pages in, and in the acknowledgments for the content of the book, turns out about somewhere between a third and a half of this book was written by Ward Silver. But the book that I have actually slept with under my pillow at night in order to try and osmose more valuable information from it is Grounding and Bonding for the Radio Amateur by Ward Silver. This is a fantastic book. The second edition has just come out, and I'm really excited tonight to be able to introduce to you the author of this book. The information that's in this book and what you're going to hear about tonight is vital to keeping you safe, keeping you alive, and keeping the noise in your ham shack to a minimum. So with that, please join me in welcoming Ward Silver.
Wow. What a great bio. I should pay more for these. This is great. Thank you. Yes, I was the lead editor and author of the license manuals and the handbook and the antenna book. For a while, I felt like I had the greens and the blues on the Monopoly board. It was really something. So I grew up reading ARRL publications, and then one day I discovered that I was writing them. So it was really quite a surprise and quite an honor. And I'm just glad it's worked out as well as it has. One book, this is my only commercial of the evening. This is Ham Radio for Dummies, 4th edition. And for those of you that are new hams and you've gotten your license and you're now wondering, what the heck do I do now? That's exactly why I wrote Ham Radio for Dummies. So everybody's a dummy about something, and I'm no different. And so I thought, why don't we just pack all this information into that book and help people with a sort of a desktop Elmer. And for those of you that have been out for a while and you came back, you're probably wondering, what the heck is all this stuff? So I tried to capture some of that in there. So keep that on your shelf and use it wisely and often. So tonight we're going to talk about grounding and bonding, surprisingly enough. That's the focus tonight. Home stations, primarily home HF stations, where this seems to make the most difference. And they're the things that I will talk about you can also apply to mobile stations, if you think about it. Okay, so what are the goals of this presentation? First, I want you to understand the difference between ground, as we use it in the United States, and bond. They're often used interchangeably. They're quite a different thing, and they're both important. And then we're going to go over 3 different types of grounding and bonding. One is AC safety, happens at 60 hertz. One is lightning protection. Lightning extends from DC all the way up into the VHF region, so it's an RF type of an event. And then RF, meaning our transmitted signals and received signals. So each of these domains, if you will, have different requirements for grounding and bonding. So I'm going to discuss the issues associated with these three different sets of requirements. I'm an engineer, so I use the word requirement all the time, and some techniques for dealing with them in the home HF stations. This is a very abbreviated version of the book, and the book and this talk are not a step-by-step how to do it. What they are is a toolbox and an explaining of the basic concepts. There's more in the book, obviously, than there is in this talk, but everybody's got a different situation. So the idea is to provide you with a toolbox and explain the basic concepts so you can go back to your station and go, I see what I could do here. I see what I could do here. I need to do X and Y. And then you figure it out within your own constraints and resources. We'll also reinforce that one common system of grounding and bonding will satisfy all three sets of requirements. You don't have to have an AC safety ground system and a lightning protection ground system and an RF management grounding and bonding system. They're all related, and by doing the right thing one time, you can satisfy all three sets of requirements. And then at the end, I'm going to provide comprehensive resources. I've already sent the PDF slides in to the club, and be happy to distribute them. They're not copyright or anything else. That means you don't have to write down all the URLs and things like that. You'll get a complete copy of the slides if you want. Okay, so here are your ham radio references. Obviously, as the editor of the handbook and the antenna book, I was able to take a lot of material from the grounding and bonding articles and publications and my grounding and bonding book and summarize them in the ARRL handbook. If you look for the station construction chapter, you'll find it there. And in the ARRL antenna book, there's a big chapter on safety, and that's where the grounding and bonding material is. Ron Block, NR2B, wrote a very good series of articles in 2002 QST on lightning protection for the amateur station, and those are available to the public. You don't have to be an ARRL member to access them, although I hope you are. And Ron recently won a QST cover plaque for describing how he constructed a grounding and bonding system for a club station in New York. And Ron has also written a book called Lightning Protection. And it's not a terribly big book, but it dives deep into lightning protection, what it is, what lightning is, and how to apply it. A comprehensive guide for amateur radio. So it starts where my book is, and then it goes really deep into the lightning protection area. But take a look at those QST articles if you want. You can just search for Ron Block on the ARRL website, or they are in the technology section under safety. K9YC, Jim Brown, has written a tremendous amount of really good material on his website, k9yc.com/publish.htm, and you will find a number of tutorials. The two that are most germane to this talk are power grounding, bonding, and audio for amateur radio, and RFI ferrites and common mode chokes for hams. So those are two very, very valuable pieces of material. Jim is a retired audio engineer and had to grapple with this pretty much daily in his professional life for many years. W8JI, Tom Rauch, his website, whji.com/ground systems, is very good. Tom lives on a hilltop, really a mountaintop in Georgia, with a 300-foot broadcast tower that he bought. And he knows a lot about lightning, and I can imagine how he learned a lot of it. So that's a very good website for you. And for those of you that are into mobile stations, Alan Applegate, K0 Bravo Golf, K0BG.com. that is a go-to website for you with a lot of really, really good information. And of course, my favorite, and this is the second edition of Grounding and Bonding, and that book covers all three of these systems, and it's been reviewed by a number of really good experts, including Ron Block, who was one of the early employees for Polyphaser Corporation. Many of you have Polyphaser protected devices in your antenna system. Ron was a reviewer of the book. Also Jim Brown, the ARL Lab, Dale Svetnoff, WA9ENA, who is a lightning protection consultant in the upper Midwest. So those guys really did a tremendous service to me by reviewing the material and making sure it was correct and appropriate, and that we mentioned the things that needed to be mentioned. It's a toolbox, as I explained before, and if you read through the book, you'll recognize a lot of the things that you can do, and then you apply your resources and circumstances to get them done. Okay, so let's jump right in here. What is ground anyway? You hear the word being used all the time, and often without really being understood in the same way that it's being spoken. It can have many different meanings. It can be a noun, which is referring to a connection to the earth, an earth connection. And when you're talking about AC or lightning protection, that's generally what you mean. It can also just be a local reference potential or voltage. For circuits, they talk about analog ground or digital ground or circuit ground. What they're just talking is the local reference voltage, whether it's a 0 volt with respect to the earth or 100 volts with respect to the earth. You don't know. It's just the reference voltage. Airplanes, for example, the avionics, they talk about the ground system, but it's not a connection to the earth, and I've never seen an airplane dragging a chain yet. So ground is just your local reference voltage. It can be a verb, which is an action, meaning to connect to the reference voltage. I'm going to ground this capacitor. I'm going to ground this antenna feed line. That means connect them to whatever you've identified as the local reference potential, whatever it is. And it can also be an adjective to describe a type of a connection, like a ground conductor or a ground system. And it can mean all these things in the same time in the same sentence. So you hear people saying things like, I'm grounding the chassis to ground with a ground wire. And all three of those words have different meanings. And you hear people talking about grounding systems, and you listen for a minute, and you realize they're talking about two completely different things, but they're both nodding up and down in the same direction. You've got to watch it. When you use this word, it's overused, and you have to make sure the other person understands how you're using it. So the British, for example, have recognized this for many years. And when they talk about connecting something to the earth, they call it earthing as opposed to grounding. And so they differentiate between an actual connection to the earth and these reference potentials, and that helps some of the confusion. Also, there's a couple of myths about the ground. The earth, meaning your backyard or wherever you are, it's not some kind of a magic 0 volt infinite sink that you pound in a ground rod and you connect whatever you connected to it, and suddenly all the current in that connection just magically disappears. And it's always 0 volts, and you never have to worry about it. And the earth is not like that. It's made out of dirt and rock, and it has resistance, and the resistance varies with where you are in the earth or on the earth or under the earth. And so current flowing through that material causes voltage drops. So you will have all kinds of different voltage potentials around a plot of ground. And so you can't just pour RF or lightning into it and magically expect it to disappear. The same goes for a vehicle body. Just because you call it ground doesn't mean it's 0 volts. So you have to remember that it might not be 0 volts. There are some real fuzzy definitions. I try not to use the term RF ground because when you say that, you think, oh, any RF circuit or current will see 0 RF volts here. And that can be made to happen for a very narrow range of frequencies. But hams have an incredibly wide range of frequencies to deal with. We go from 0 hertz at DC all the way up into the microwave region. So the RF ground, it may be 0 volts, say, over a few of the lower HF bands, but below that and above that, it could be anything. So you have to be very careful when you use the term RF ground that you're just talking about what frequency and what kind of currents and voltages are we talking about here. So I just generally don't use the term. Also, ground loops. If any conductive path around in your station between two pieces of equipment that has two different cables going through it, and you can trace a conductive path all the way through, that's a ground loop. And even a modest size or to small station, if you go around and look in the back of your equipment, have you ever looked at the back of your equipment? There's dozens, if not hundreds, of ground loops in most stations, and you're never going to get rid of them. You can manage them, and we're going to talk about that later, but they're not automatically a problem. Power guys don't like ground loops because they enable large air currents to flow. I understand that, and so they don't like ground loops, and they will break ground loops specifically to prevent that from happening. Also, audio guys don't like ground loops because if you have a loop and there's a magnetic field going through that loop and that magnetic field is changing, that loop will pick up voltage proportional to the area of the loop, and it will cause a current to flow in the loop. For example, if you put a loop of shielded cable around a power transformer that's radiating some 60 hertz magnetic field, it will pick up that field and cause a current flow in the shielded cable, and you'll hear hum at a 60 hertz sinusoid. So that, in that case, a ground loop is a problem. And so you might want to use a ground buster. But up in the ham station at the frequencies we operate at, there are going to be dozens and dozens of ground loops. So they're not the problem you think they are. Also, single point ground. Single point means electrically small, so that everything connected to this structure, whatever it is at the same voltage. So that's primarily a concern for electricians who don't want to have ground loops. So they connect everything to this single point. And it's electrically small. What does that mean? It means much, much, much less than a wavelength. What's a wavelength at 60 hertz? 50 million meters. Okay, so you can have something the size of a building or a football stadium, and still it's electrically very small. So what you want is to be careful when you use that term. You don't really want to be running the long conductors in your ham station over to this point just because it's a single point. What you're creating is big loop areas. And when you create big loop areas, you pick up RF fields, magnetic fields, things like that. So be careful about the term single point ground. We're going to use the term when we talk about single point ground panels later in the presentation, because we want everything to be mounted on this one panel, and I'll explain why in a minute. But each one of our sets of requirements, AC, lightning, RF, uses the term ground differently, so you have to be careful. Let's jump over to bonding. Bonding, if you look it up, it's a connection intended to keep 2 points at the same voltage. That's it. No fancy other definitions and sub-definitions and qualifications and all that kind of thing. It's just a connection between 2 points to keep them at the same voltage. If you do that, they're called electrically bonded. The whole point of bonding in your station is so that everything in the station goes up and down together. And you'll hear me talk about this all the time. Everything going up and down together, either because of RF pickup or because of AC fault current or because of a lightning strike nearby. When everything goes up and down together so that it's at the same voltage, that prevents shock hazards from voltage differences. If everything's bonded together and you have an insulation fault or a power cord failure or something, and you don't get this piece of enclosure being at a different voltage than this piece. And when you have that happen and you touch both of them, you can get a shock. So by bonding them together, you zero out that voltage difference, you reduce the shock hazard from voltage differences. It also prevents destructive voltage differences caused by lightning surges. When you get a big lightning transient of current, either through your station or even nearby, so that it has a strong magnetic field, what you can get is a very substantial voltage difference between these pieces of equipment. Only for a short time, but that's enough. Electricity is really, really fast. It doesn't need much time to cause current to flow. Why does current flow? Because there's a voltage difference. And if you can zero out the voltage difference so that everything's going up and down together from that lightning surge, then there's no current flow between the different pieces of equipment. And that's what causes the trouble. It's not the voltage, it's the current. But the voltage causes the current to flow. So by minimizing voltage differences, you minimize current flow. And that leads to the third point up, the fourth point up there, that RF pickup in your station from the nearby antennas, that causes current to flow between the devices in your station. Why? Because it induces a voltage difference between the different pieces of equipment. And that's what causes RFI, is that current that flows because of the voltage differences between the pieces of equipment. If you can minimize that voltage difference, you minimize the current that flows, and that minimizes RFI in your station. So bonding is good. So for bonding to work, it has to be low impedance. You don't want impedance in your bonding conductors, because if you do, and you have current flowing in that bonding conductor, then it'll cause a voltage drop, and you don't want voltage drops. So your bonding conductors have to be as low impedance as possible, and it has to be electrically short so that it doesn't start acting like a transmission line. If you have just a regular piece of wire connecting points A and B, and it's very, very, very short compared to a wavelength, it will act like a 0 ohm connection. But as the frequency goes up, the wavelength goes down, and that piece of wire, the same physical length, it gets longer and longer and longer in terms of a wavelength. If it gets up to 1/8 of a wavelength, then it starts acting like an inductor. That straight piece of wire that was 0 ohms at one frequency, at higher frequencies, it becomes inductive. It looks just like an inductor. And if you go all the way to a quarter wavelength, it actually acts like infinite connection impedance. There's no conductivity between the ends of the wire because it's a quarter wavelength long and it's resonant. And then you can keep going to 3/8 of a wavelength that acts like a capacitor, even though it's a straight piece of wire. And then you have to go all the way around to half wavelength before it starts acting like the 0 ohm conductor again. So got to keep them short, electrically short. This conductor has to be heavy enough to carry the expected current. So if you're just grounding within the station, you might not need a very heavy wire to get the job done. If you're talking about grounding for AC safety, the rule is, according to the building codes, is that conductor has to be capable of carrying all of the current supplied by the branch circuit. So if you have a 20 amp breaker on that branch circuit your ground conductor to everything that's powered by that circuit has to be capable of carrying enough current to open that breaker. That's the whole point of that conductor, is to cause the protective devices to trip and remove power from the circuit. So it has to be heavy enough to carry that current. If it's a lightning protection conductor and you expect lightning surges to go through it, it's got to be heavy enough to handle that stuff. You're talking about kiloamps, which to a circuits guy like me makes me really nervous to talk about kiloamps. A small wire hit with a kiloamp, poof, it makes a nice green lightning bolt for a second, and then it's gone. So this is why your building codes say number 6, number 2, number 4, whatever. And it also has to be sturdy enough to survive the environment. Inside your station, that's not a big deal. But outside, where you're talking about connecting to ground rods, where you're talking about running radials out from a tower or something like that, it has to be heavy enough to survive being driven over, dug up. Don't ask me what happens when you hit it with a rototiller. It's got to be heavy enough to let you know that you're digging up your ground system. So, and when you hit a big wire with a lightning pulse and a kiloamp type surge, that wire is going to try to move. And you can get 500 pounds per foot in a typical lightning strike. It's called the Coulomb force, and it's caused by the magnetic field of that current flowing through the wire. And that's why when you look at your building code, they specify that ground wires running along a foundation have to be secured to that foundation, because otherwise, if you get a big fault, that wire is just going to tear itself apart. There's some really great and interesting YouTube videos on that. So what do you do inside your station? The standard for commercial and military installation is strap, copper strap. In a ham station, we can use copper strap, we can use aluminum strap. It should be 20 gauge. It should be at least an inch, maybe an inch and a half wide. You can also use heavy wire. All that N0AX, all those little bits from your wiring that you cut up and you said, I'm not throwing this away. This is perfectly good wire. I'm not getting rid of it. And it's all in a box in your garage. I know it is. So this is perfect for that. Use the heavy wire that you saved, and that makes a really good grounding conductor. It's interesting to note that as a strap gets wider and wider as you run alternating current through it, the same kind of effect that causes a skin effect at RF causes the current to separate and only flow along the edges of that strap. So getting much beyond an inch or an inch and a half wide strap doesn't buy you a whole lot. And that's why a heavy round wire like number 14 or number 12 will work just as well. If you have equipment that has to move around, you can use that flat weave 10 braid that you can find at automotive supply stores and sold by a lot of many vendors at Hamfest and things like that. It's silver colored. All the little wires are tinned, and then it's woven into a flat braid that's maybe 3/4 or an inch wide. That works real well, but you have to protect it from moisture and chemicals because it's not made to get wet. If it's going to get wet or be exposed to chemicals, all the connections between those little wires, they start to corrode. And when they start to corrode, you have diodes and all kinds of nonlinear junctions, and it becomes a pretty effective noise generating device. So protect it from moisture and chemicals. If you go to the auto parts store, you can buy these braid straps that are actually protected by a plastic jacket, just like coax is. And those are for use in your car. Typically, you can use this braid without protection in a typical ham shack as long as you keep it dry. Don't use exposed braid from old coax. I know we've all done it. I used to do it. You say, well, I got this old piece of coax. It's no good at RF anymore. But, you know, that braid might make a really good ground conductor. So you strip the jacket off, and you loosen up that braid and you slide the center conductor out, and use that for high voltage, I know. So here's your braid, and it's this nice shiny coppery stuff, and then you flatten it out and you use it as conductor. Don't do that. Why? What is that jacket for? That jacket does two things. It holds all those little wires firmly together so they're in good contact with each other, and it also protects them from water and oxygen. Water and oxygen and copper cause corrosion. And so what happens is when you take that braid out of the jacket and you loosen it up to get it off the center conductor, then it immediately begins to degrade. And after a while, it's not effective at RF as much as it was. So if you want to use that old piece of coax for something, just leave the braid in the coax, strip it at each end, waterproof it, put a terminal on it, and just use it as what I fondly call a BAW. That's a big ass wire. Okay, so you just have a nice big piece of wire that's as thick as a piece of coax with a terminal on each end. Works great, but don't strip the braid out and use it. Bonding, when you do it like this, and I haven't talked about any special conductors or anything like that that's really expensive. When you do it like this, it works in your favor for all three of those sets of requirements: AC safety, lightning protection, and RF management. Let's talk about AC safety grounding for a minute. Grounding for AC safety, depending on how old your electrician is and where you are in the country, it could have any one of several common names. The current common name that's used in all the standards is equipment ground. When you talk about equipment ground, that's a connection from your equipment to the central AC service grounding point. It can also be called third wire ground because that's the third wire in the power plug. It can also be called green wire ground because these wires are often green. That's the standard for insulation to indicate that you have a ground connection here. Got to keep your ground connections when you're talking about AC safety. The most important thing is they be low resistance. Remember, I talked about that ground connection has to carry enough current if there's a fault so that the protective device at the other end will open up and remove power from the affected circuit. And that's to protect you, and it's to protect your equipment, and it's to protect your building to keep a fire from starting. Okay, so low resistance is what you want for AC safety grounding. This only has two purposes. One is it provides a path back to the AC common point for fault current. That includes short circuits and it includes leakage current. Say you have an old radio or something and a bypass capacitor is starting to break down and it allows some AC current to flow through that chassis. You want that leakage current to flow back to the AC common point and not be present as a voltage on that piece of equipment, so you would get a shock. So it's going to provide a path back to the AC common point, a low resistance path, and all of these earth connections, not only yours, but if you go out and you look at the power poles, almost all of them will have some big heavy ground wire coming down the pole. It could go to an actual ground rod, or it can be just wrapped around the bottom of the pole. It's called a butt wrap, and you put the pole in the hole, and that's how the ground wire connects the earth. All of these thousands upon thousands upon thousands of ground connections, they're not necessarily all that good, but there's so many of them in parallel that they stabilize the AC power system voltage during faults or transients such as lightning or accidents or something falling on the lines. You don't want the whole system going to crazy voltages because it loses its ground reference. So you provide this ground reference, this reference potential along the surface of the earth, and that helps keep everything stable. Okay, now I know, we're all licensed, FCC licensed radio amateurs, so we pretty much know everything, right? I mean, that's we got a license. So, well, maybe we don't know everything, huh? So I think most of us could run a branch circuit. Some of the more advanced students in the class could run a three-way light switch. But there are so many different things that you can go down to this hardware store and look at the electrical section. And there's dimmers and controls and multi-point this and multi-point that, and all sorts of stuff that you are not going to be familiar with. So get some kind of a reference that tells you how to do this. So I like this one. This is the previous edition to the ones on your screen. It costs less than 20 bucks, and it's got all kinds of pictures and instructions and all these things to do, and most importantly, to not do when you do AC wiring. And so get this book, use it. You can hide it so none of your friends know you're looking at a reference book. But these are really, really good. Okay, so all of these rules and stuff, they come from the National Electrical Code, or NEC. If you go get a copy of the NEC, it's a little book. It's only about yay big. It's about yay thick. And if you open it up, it's a bunch of obscure rules that say you shall do this and you shall not do that. But that's it. They don't really tell you why. Okay, so if you want to know why, and most of us would like to know why, what's the rationale for this rule? What are we trying to accomplish? So you go get a book like this one. This is called the NEC Handbook, and it's available at your library. The new edition comes out every time there's a new edition of the NEC. And these are not expensive, surprisingly enough. You can buy them online, a used copy for 30 or 40 bucks. You don't really have to. What concerns hams for the most part is article, meaning chapter, Article 250 on grounding, and Article 800 on antennas. And this book comes with all kinds of pictures and charts and how-tos and arrows, and explains what the rationale of the rule is. So if you want to know why you're being told to do what your building code is telling you to do, then the NEC handbook is what you want. Okay, when you do a branch circuit, and a lot of us put in a sub panel in our station, in the garage, in the basement, out in an outbuilding or something like that, there are special grounding rules for sub panels. If you follow them, you will not present a shock hazard to yourself if there's a problem at the sub panel or any of the circuits supplied by the sub panel. People are electrocuted every year because the sub panels are not grounded properly. And so what happens is you create a fairly substantial electrocution risk. Just standing barefoot on concrete, for example, and touching something that's electrified, concrete is way more conductive than you might expect. And people are electrocuted all the time. Follow those rules when you put in a sub panel. Finally, it's not a bad idea, unless you're really experienced, to hire an electrician to come over and look at what you've done. And they may say, good job, well done, where'd you learn how to do that? Or, I don't think you want to do it this way. And that could be solid gold advice to protect you, protect your house, whatever. So have somebody come over and take a look. Remember, your local code is the law, and it's called the authority having jurisdiction. It might be your city, the county, whatever. That local code is the law. And so you need to try to follow it as best you can. We can't always follow it. Maybe we make a mistake. Maybe we just decide we don't have the money to do it. It's your decision, okay? But local code is the law, and it's there not just to make your life difficult, it's there to make your life longer. And all these codes in the NEC are written by the National Fire Protection Association, and that ought to tell you a lot right there. Okay, enough about AC safety. Let's talk about lightning. Lightning comes from way up in the sky, 50,000 feet. something like that. There's a big charge imbalance between way up there and way down here. So when lightning starts to make a journey and the charge starts to flow, it's flowing over a distance of, 6 to 10 miles. You're not going to steer it, okay? You can't force it to go over here or over there. It's going to go where it wants to go, okay? But you can help lightning make good decisions. You're not going to steer lightning. You're going to help it make good decisions in getting to where it wants to go. Where does it want to go? It wants to go, hang on a second. I've got an inquisitive cat. I can't steer the cat either. Okay. What does lightning want? Lightning wants a heavy, direct path to the earth to dissipate this charge imbalance in the ground. So the charge is going to spread out and go into the ground, or it's going to come from the ground and flow up through the strike to where there's less charge, and so it equalizes the charge imbalance. It wants a heavy, direct path. Okay, remember we talked about lightning goes from DC to way up in the UHF spectrum. So it's an RF event. It's an AC event. And in that case, inductance is more important than resistance. AC safety, you want low resistance. In lightning protection, you want low inductance, okay? The voltage across a conductor is proportional to its inductance. The more inductance you have, and depending on the rate of change of current, that causes the voltage across a conductor. Let's take a piece of number 12 that's 1 foot long. And if I hit that with a current surge that is changing at the rate of 1 kiloamp per microsecond, okay? So that's a pretty fast change, but that's typical for a lightning pulse. 1 kiloamp per microsecond across this 1 foot piece of number 12 wire will create a potential difference of 761 volts. That's a straight piece of wire. It's not doing anything. It's not connected to anything. It's just sitting there. And if it has a current pulse like that going through it, you'll get 700 plus volts across it. So minimize the inductance. That's much more important than resistance. That's wide, direct paths. All of these paths should be outside your residence, okay? Outside. Don't run them through the crawl space. Don't run them through the attic. Don't run them through the walls. Don't run them through your station. Help lightning decide to get to the earth outside your residence where it's safer. Don't make it easy for lightning to go through your station on the way to the earth. It doesn't care. It's just looking for a path to the earth, and it's no different than any other current. So if there's a current path there and it's low impedance, then lightning's going to flow on that path. You don't want that path to be through your station. Okay, so I mentioned single point ground panels. Excuse me. Okay, there's that term, single point. Okay, we're going to see a drawing of this in a minute. To help the lightning get to where it wants to go, with a minimum of flowing through your house and your station, you use a single point ground panel or an SPGP. The idea is all of the entry paths from the cables that come from outside the station, they all go to this same panel. And it bonds the grounds of all those entry paths. If you have a PL259 and you have a bulkhead connector there and it's mounted through a hole in the panel grounds that shell because that panel will be connected to an external ground conductor. That's what your perimeter ground is. It goes around the outside of your residence. It may not go all the way around, but as much as you can, you've got a ground system outside. So you bond that panel to the ground system. And everything that comes in from the outside goes through a protector of some sort, and that protector is grounded to the panel. So all of your protectors that are mounted on that panel, when the lightning surge comes, they all fire at the same time. And I was not sensitive to this until Ron Block explained it to me. I said, wait a minute, you want them to fire at the same time. It's not enough to just have protectors all over the place. You want them to fire at the same time. Remember, we talked about the destructive voltage differences where suddenly this part of the station is at this voltage and later it's like this. That's a destructive voltage difference. If you can put all your protectors in the same place, grounded to the same panel, they will fire at the same time and everything goes up and down together, not up over here and then 10 microseconds later up over here. That's plenty of time for a destructive voltage difference to cause a problem. So all of your protectors fire at the same time. That's why they're all mounted on this panel. That includes non-RF and AC power. So if you've got like a phone line, you got a telephone line, you've got your AC safety ground, all this kind of stuff. All of this stuff needs to be bonded to this panel, or at least to your perimeter ground system. Okay, so when I talk about protected and unprotected cables, here's my cursor. You can see it flying around up here. Here's a single point ground panel. It's just a big piece of metal. Typically, it's a big piece of aluminum. And you mount all of your lightning arresters on that piece of aluminum. You mount a protector for your data or phone service. You mount a protector for your rotator or your control line. You even mount an AC power protector, sometimes called a protected line duplex output. And basically it has protectors in it. So you run a branch circuit from your circuit breaker box over to this AC power protector that's on the single point ground panel. And then you run another cable that goes into your station and supplies your equipment. Most stations can run from a single branch circuit. I think most of us have thought about this, and maybe we have one breaker in our service panel that says radio or something like that. You can pretty much run a bunch of computers and a bunch of 100-watt radios off of one circuit. If you've got amplifiers, you would run a separate circuit for them. Okay, so as you can see here, these are all mounted on the panel. The panel is connected first to your station ground bus inside, and we're going to talk about that in a minute. Also to your outside ground system. Now that might be one or two ground rods, like right here. If everything is together, you might have all your ground rods together. But it's recommended that you run several ground rods and a buried conductor all the way around the outside of the house as a protective kind of a ring. Now, if you've got a concrete driveway or something, you can't bust up the driveway to run it through there. So you might make an open ring and skip the driveway or the patio. That's common. The idea is just to get a lot of wire and ground rods in the earth to provide this big, heavy, direct path to the earth for the charge to dissipate. Each one of these services, when you have the technician come, they are required to establish a ground connection. They will look for your home ground connection, and if they can mount everything over there by the service panel, they will. If they can't, they will drive in their own ground rod. So you basically tell them, hey, look, I got this nice perimeter ground system here. Please connect your ground terminal to that system. Okay. Now, you want to keep the protected and the unprotected cables apart. I know it looks a lot better if you have one big cable bundle with nice tie wraps and all this kind of stuff. You don't want to do that, because if lightning comes in on any one of these and it's bundled with these, it'll happily just jump from these to these and bypass your protection. So keep your unprotected cables away from your protected cables. Run them through different conduits, run them one from above and one from below or side to side. Whatever you got to do, create that big air gap between those two sets of cables. Here's an example of a single point ground panel for station entry. This is my friend K4RO's. installation at his house. He's got one of those houses where he's got a garage underneath and the house is up here. And you can see he's got this big panel mounted on the side of his garage. His station is up here someplace. So all of these antenna system cables, they come in and then they go up into his station. Before he installed this panel, he lives on top of a hill. He's got a great station. He's got a tower up on the hill. Every time a big thunderstorm would come through, he'd lose something. Something would get blown up in his station. And finally, he just said, that's enough of that. He put in this big panel. Here's his BAW, his big-ass wire that goes outside to ground connection. And he's mounted everything associated with the antenna system on this panel. You can see a stack match. You can see antenna switches. You can see filters. You can see all kinds of stuff. Since he has done this, he has lost exactly 0 pieces of equipment, 0. So he's a happy camper, and that's bonding everything together on this single point panel so that all the protectors and everything goes up and down together so there's no destructive voltage differences. Here's an example at my station. I have three 60-foot towers running along a high spot between a couple of ravines. And I know these things get hit by lightning. I've seen burned trees and all this kind of stuff. So at the base of each tower, in a surplus electrical fiberglass box, I've established a single point ground panel at the tower base. And you can see an RCS4 current coax switch here. This is an L version, which means it has a gas discharge tube on each one of these antenna lines and the incoming hard line here. You can see that it's mounted on this big piece of aluminum flashing. That's all it is a roll of aluminum flashing at the store. I didn't go buy special plate. It's not heavy. It's not expensive. It's just roof flashing. You can get it at any store. Maybe your brother-in-law who's in the roofing business can give you his scraps, okay? Just mounted it on a piece of plywood and bolted it in this box. And so here comes a buried hard line from the station, and the antennas come out from here. Here's the ground wire right here. And now I'm going to save you some serious money. And everybody's like, what? He's going to save money? Okay, so instead of that fancy rotator control cable with the 2 number 16s and the rest of them are number 18, it costs like $1 a foot now or more, go out and get irrigation system control cable. This is a 10 conductor, they're all number 18, multi-conductor cable. It's in a PVC jacket here that's rated for direct burial, and you can double up 2 pairs to make those heavy pin 1 and pin 2 solenoid connections on the standard rotators. And it's solid wire, so you have to take special care to put terminals on it, or you can just do away with the terminals and just loop the wire around the screws. But connect them with a gas discharge tube. That's what these little guys here are. The lowest voltage you can get is about 75 volts. So I've got a 75 volt gas discharge tube. All I did was take a sheet metal screw, punched it into the aluminum flashing and connected it to this terminal strip right here. This stuff, this wire is way, way cheaper when you buy a big spool of it than the special fancy rotator cable. Save the rotator cable for the little rotator loops and the parts that go up the tower or inside your station. This stuff is way cheaper and it's just as effective. Okay, let's talk about lightning protection and this perimeter ground system. If you don't have all of your subsystems, your electrical panel, your telephone system, your entertainment system, you put an antenna on the roof and you grounded it like NEC says, plus whatever else you've got in the house. And they're all connected to these ground rods outside. What happens if you don't have, what happens if you don't have this big wire connecting all the ground rods together? What are those ground rods connected together with? Dirt, okay? dirt has resistance. If you took a resistance meter and you measured between these ground rods, you might measure 10 ohms, 20 ohms, 50 ohms, 100 ohms. What happens if you have 1,000 amps from a lightning surge? It doesn't even have to hit your house. It'll just flow through the earth as the charge rebalances. What happens if you have 1,000 amps flowing for a short period of time through the earth between two ground rods that have 10 ohms of resistance between them? Well, 1,000 times 10 is 10,000 volts. And suddenly you've got 10,000 volts between your phone ground system and your home entertainment system ground system. And what happens then? Well, that's when you hear stories like, I was sitting there minding my own business and there was a lightning flash outside and a big green arc went from my home entertainment system to my telephone, and now nothing in the house works anymore. That's because the ground systems were not going up and down together. One ground system went much higher than the other. It may have actually equalized after a while, but for a long enough period of time, there was 10,000 volts between them and destructive voltage differences in currents. So you beat that by running a big heavy wire. Check your building codes. Number 6 is typically the smallest between all of your external ground electrodes. And the NEC is unequivocal on that. It says all external ground electrodes shall, S-H-A-L-L, be bonded together. And there is no wiggle room in shall. You absolutely have to do this outside. If you have more than one ground rod, get out there and bond them together. That's called your perimeter ground. Everything outside that's connected to the earth is bonded together. So what happens here if you don't have everything bonded together? All right, here's the lightning, and you've got a tower and some feed lines, and you've got an entry panel, and it's got a ground rod. Sure, that's great. It's also connected through the panels to your radios, and they're powered from this branch circuit, and you've got your AC service entry over here, and it's got its own ground rod. Well, these aren't connected together, so here comes the lightning, and it flows along here, and it says, oh, looky here. Well, there's pretty good ground connection over here, but by golly, there's also a fairly low impedance path that goes over here to this ground rod. So not only am I going to cause a voltage difference by flowing through the dirt, I'm going to flow through this radio station on my way to the other ground rod. And that causes lots and lots and lots of damage. So you want to not have this low impedance path through your station. You want it to be outside your station. So here's another example. This time the lightning hits the AC power line. That's pretty common too. Here it comes, and it comes to your AC service entry, and it sees this ground rod right here connected to your service panel. Bunch of it goes there. It says, hey, where do these other things go? So here we go. This is unprotected AC. This is the branch circuit that you run all the way over to your single point ground panel, and you've got a protector over here. Okay, so that protector helps the lightning go outside and find your perimeter ground. So it sees this great, terrific, heavy, direct path to the earth outside your house, okay? And it doesn't want to flow through your radio station on the way to the ground. Give it this big, heavy, direct outside path. It's a lot of work. You got to pound in the ground rods or get one of those ground rod drivers or something. And then you got to go through and connect all the ground rods together. It's worth it if you want to protect your station and you get lightning from time to time. So ground paths should go around your station. If you've got a tower, and you've probably seen this in the handbook, you're looking down here on a lattice tower like Roan 25 or something in a concrete tower base. The handbook and other references have told you for many years to take each leg, connect a galvanized clamp so that you connect a copper ground wire from here over to a ground rod near the base. and do that for each leg. And then you connect each one of the ground rods together with a ground ring of heavy wire. That's good. That makes a really good ground connection. As long as you got the guy with the backhoe out there, have him make some more trenches. They don't have to be 6 foot deep. Make a trench to lay more of that heavy wire in with a couple more ground rods about 30 feet from the tower. So you wind up with 3 radials stretching from the base of the tower. And that makes a very effective tower ground. On the tower, you want to bond your feed lines to the tower every 50 feet. So if you've got a 50, 60 foot tower, you bond at the top, you bond at the bottom. Why do you do that? Remember that number 12 wire with the kiloamp current in it that had 761 volts from end to end? A 50-foot tower can easily develop 100,000 volts if it gets hit by lightning from the top to the bottom. And if your feed lines are not bonded to the tower, so remember, everything goes up and down together, and suddenly your feed line, well, the tower's at 100,000 volt and your feed line's down here. I don't know too many coaxial cables that jackets are rated for 100,000 volts. So what happens is the cable is destroyed, or you get pinholes, or you get splits in the jacket from the various arcs. So you want to bond your feed line to the tower every 50 feet using some kind of a bonding bracket or a bonding kit from a hardline manufacturer. And yes, it's a pain in the neck. And you got to put extra connectors on it, and you got to waterproof them and all that stuff. But that keeps your system intact when it's stressed out by a lightning strike, either direct or nearby. If you've got an insulated base tower, all of my towers are insulated. They sit on fiberglass insulators. So what I made is a little spark gap of heavy wire, and the spark gap just is 2 wires that cross each other. They're very close, but they're not touching. And you just move them back and forth, just like gapping a spark plug. Some of us remember gapping a spark plug. So you want about 1 millimeter for a 3,000 volt voltage protection. The reason I do it this way and not this way is that when the wires cross at an angle, the rain does not accumulate in that gap. Insects don't build nests in there, and that would cause short if there was a lightning strike. The lightning comes along, it builds up the voltage, it arcs over between those wires, it discharges the tower into your ground system. So that's a way to protect an insulated base tower. Okay, RF management in your station. The first thing you have to remember is everything in your station is an antenna that conducts electricity. That includes all your feed lines, your RF bonding, your protected power, your unprotected power, your safety ground, interface cables, bike cables. You are also conducted, so you're part of this. And why do we pick up so much RF? Well, think about it this way. At HF, let's say you have a 40-meter dipole in the backyard. And what's the wavelength at 40 meters? That's a trick question. It's about 120-something feet. If you're closer than 120 feet to that antenna, and most home stations are, you're in the near field of that antenna. You are electrically really, really close. And a lot of us have antennas on the roof. We have antennas in the backyard, all this kind of stuff. Electrically, they're really, really close. So we're going to get a high RF field in the station unless we put a Faraday cage screen around the station. That doesn't happen very often. So basically, everything that's a conductive material in your station is going to pick up some RF. So there's no way you're going to beat that. You just have to deal with it and manage it. So number one, forget about creating some magic RF ground point that you can connect everything to this one point and all the RF goes into that point and disappears. You don't have any problem. Forget it. It's not going to happen. Concentrate instead on bonding all your stuff together. Boy, I'm doing this a lot, aren't I? So that everything goes up and down together, whether it's AC or lightning or RF from your transmitted signal. You want it all going up and down together so it doesn't cause current flow between these pieces of equipment which causes RFI and all kinds of other problems. You want all these connections between these pieces of equipment to be electrically short. So short, direct wires, and it keeps everything at the same voltage. If you put in an amplifier, you get an even higher RF field strength than from a regular transceiver. And you get to meet the neighbors too, but that's different. That's a different kind of bonding that you have to do with your neighbors. But that'll mean you have to have extra attention to bonding in your station. So a good way to do that is to create a common, what I call a reference plane or a grounding bus. And a lot of us have already done this to some extent in our station. You've seen this picture a million times, maybe in a license guide, maybe in a handbook, whatever, that there's something here. Usually it's a 1/2-inch copper pipe because that's the cheapest they've got at the store. And then everything is connected to that copper pipe. I mean everything, even the antenna switches should be connected to that copper pipe because they are exposed metal, just like a keyer or a computer or a transceiver. So you do not want that exposed metal to suddenly go up to a lot of volts. So you bond that to this copper pipe. Do not use hose clamps. Everybody uses hose clamps, and you put the clamp around it, and you screw it down tight. It immediately begins to loosen. Hose clamps are not designed for metal-to-metal contacts. That's why they're called hose clamps. They're designed for flexible plastic or rubber material to compress it around probably a metal, some kind of hard surface, a tube, whatever. And so they hold that flexible material on the tube. They're not made to do metal to metal. So you can use a sheet metal screw with a lock washer, or you can use ground clamps. A 1/2-inch copper pipe is the same diameter as a 1/2-inch ground rod. So go out and buy a bag, what they call contractor's pack, in the big box stores of acorn clamps or whatever, and use the right stuff. It's right behind your station here, and each one of these little connections is a wire or a piece of braid or a piece of strap. And then you have one strap or wire that goes out to your Signle-Point ground panel. That was the connection we saw before. It said to the station ground bus. So what does this do for you? By connecting all this stuff together, you eliminate these hot spots. We've all had that experience, that fun experience of touching our nose while we're transmitting with a metal microphone, and suddenly you get an RF burn. That's a hot spot. It's a high voltage spot. And we want to minimize high voltage spots. We want everything to be at the same voltage, no hot spots. So we bond everything together. It also reduces buzz from rectified current from power supplies and other things, and also hum from picking up magnetic fields from power transformers and stuff. And this reduces the RFI in your shack. It's not going to make, there's no magic zero RFI solution here, but it will minimize the RFI by minimizing voltage differences, minimize the current flow, and common mode current on cables and all kinds of stuff. So it just reduces the interference. And it reduces the sensitivity to physical configuration. So you don't have to move your equipment around. I can't operate 15 meters unless I put the SWR bridge up here. If I don't, I get a hot spot. We've all experienced that kind of thing. When you bond everything together, the station is one solid electrical conductor, and it all goes up and down together. When you look around at the cables in back of your station, you cannot eliminate ground loops, so don't try. What you want to do is minimize the area. The bigger the loop area, the more voltage it induces in the loop and the more current that will flow in the loop. So by minimizing the area, you minimize the voltage and current. So use the minimum cable length that you can and try to keep from just dangling them all over the place. Kind of bundle them together. Short, coiled up cables. And I was told that if you wind the cable, if you coil it up this way in a figure 8, the inductance of each half induces voltage that cancels. And so you wind up with a minimum amount of voltage. Otherwise, if you just coil it up, it acts like a sort of an air core transformer to whatever it's picking up. So wind it up in a figure-8 shape, and you'll minimize the amount of voltage these things pick up. Use a bonding bus like we just talked about, or a reference plane. I'll show you an instance of that in a minute. Always use shielded cables so that if you do pick stuff up, and you will, then the current that's flowing on the outside of the shielded cable, not the inside, the outside, will go to a grounded enclosure, and then it will be bonded together with everything else. By bonding stuff together, you minimize that current, and what current there is does not cause voltage differences. Short straps or wires for all of these connections is also important. Okay, here's an example of a reference plane. This was a station. This is one of my operating positions previously at the station. This is just a Costco banquet table, and I have this big roll of aluminum flashing, and I just rolled it out along the tabletop and used sheet metal screws every foot or so to hold it flat and hold it onto the top of the table. And then I laid the copper pipe and held it down with clamps on the back, and all of my stuff is connected to that copper pipe. And all of the cables between all this stuff are laid down on this reference plane. And the reference plane prevents big voltage differences from occurring, so that when an RF wave comes in, it's kind of shorted out, is the way I think of it, by this reference plane. So that means much less energy available to be picked up by these cables. So by laying the cables on this grounded surface, you minimize the amount of energy they're going to pick up. Here's what I've taken to doing recently. I set up some tables for a station in the basement, and so here's the aluminum flashing. I have a big roll of aluminum flashing. Okay, I can keep doing this for a while. Put the flashing on this table. You can see the screws that I use. They're called lath, L-A-T-H screws, because they have a nice smooth head to them and they don't catch on stuff. And then I use for the connection, instead of that copper pipe, what I did, I went and bought a bunch of these ground bars that go into the AC service panels. And if you open up your service panel and take off the thing so you can look at all the wires coming in, you will see these kind of things on each side of the panel. And they're made to do exactly what we want. They have a nice big heavy screw. They have a hole for you to put the wires in, and you can torque those suckers down and it will be tight. Okay, and so you just bolt this directly to the aluminum panel with a screw, and you put a lock washer, a tooth lock washer under every screw so that it bites in to the aluminum, both of the reference plane and of the grounding bar. Use tooth lock washers whenever you can. And then from some convenient spot at the on the reference plane, here's my BAW. We all know what that stands for. That goes to my perimeter ground system, which is just outside the station. A sheet metal screw, there we go, sheet metal screw, and a stainless steel washer, and a tooth lock washer, and that holds this big terminal down on here, and that's a good, solid connection. Okay, ground system review. We're just about done. I hear the cheer. Okay, a single solid ground system made of short, heavy, direct connections satisfies all of the requirements for AC safety, lightning protection, RF management, and clean audio. You know, we got a bunch of FT8 and other digital mode operators here. A lot of the times we're sending microphone level audio into the radio with our FT8 modulation. You want that to be clean so it doesn't show up as buzzy sidebands on your signal. Your ground system is important for helping you keep audio clean. Bond all of your grounds and keep your protectors together wherever they are. And you can have multiple entry panels. You can have one at the base of your tower. You can have one in some kind of switching rack outside the house, and you can have another one inside your station. Keep all of your protectors together. So wherever that surge goes, they all fire at the same time, and yep, everything goes up and down together. All of your ground electrodes shall be bonded together outside the house. Buy a spool of number 6 and split it with your buddies. I know copper is expensive right now, but that's what you got to do to develop a protective ground system. And your perimeter ground system that you build with these bonded ground wires, ground rods, keep the lightning currents out of your house. So the lightning comes down, the current has this great path out into the earth, not through your station. Here's some additional resources. And like I said, I sent the PDF slides to your club, and you can post them on your website, whatever. National Fire Protection Association, they've got a lot of good stuff in there about electrical safety. International Association of Electrical Inspectors also has good information. Mike Holt Enterprises, Mike Holt was an electrician, and he developed this website to train other electricians. So lots of tutorials, lots of explanations, and this is a good place to go and look and say, how do they really do it? You can look on Mike Holt's website. And Polyphaser, they've been sold several times, but they're still out there under the original name. And if you look under their resources, they have white papers on all these different means of lightning protection, including for amateur stations. Both Ron Block and his brother were hams, and so they knew what hams are up against. We have these incredibly wide frequency range to protect our equipment against. And it's something that very few other services have to deal with. And here we are on our own as individuals without commercial and military budgets, and we still got to protect our stuff. So there's a bunch of good white papers on that. Here's the standards. If you really want to get into the standards, Motorola wrote one called R56, and it's for their communication site. Primarily, it's VHF and UHF. What's going on inside these buildings that you drive by with all the cables going in and out? Well, this standard describes that. You don't have their budget, but you can look at this standard and you go, okay, I get it. I see what they're doing. I'll do it my way with my resources. FAA document on practices and procedures. This is how they bond their communication stations out in the field and build them and ground them and wire them up. Good stuff. You paid for it. It's free. IEEE Standard 1100 is very much not free, but it's about AC safety, and you can find those in the library or get copies on interlibrary loan. Mill Handbook 419 is really good. This is the one I go to most of the time. It's 419A is how they ground bond and shield their electronic equipments and stuff. And they talk about perimeter grounds, and they talk about how far the tower can be from the perimeter ground, and what do you do in this case, and what do you do in that case. This is a very good standard. So if you're really interested in this stuff, or if you just want to settle an argument with your friends, these are the standards to go to. There's some books and online material. Ron Block, The Grounds, and then I showed you his new book. I just wrote a review of it in QST. This is the one, Lightning Protection, a comprehensive guide for amateur radio. Good stuff. KA Rand, Lightning Protection and Grounding Solutions, Polyphaser, and the ARL Technical Information section on the website. It's one of the great unsung resources of amateur radio. There's tons and tons and tons of material in there. Go to the technology tab and start drilling down on the website. Look for electrical safety, grounding, lightning protection. And there's lots of articles, pictures, photos, all this kind of stuff to help you do this right, along with my book. And, I did the book on contract to ARL. So even though I'm pushing it, I'm not getting any more money out of that. I want you guys to all have access to this good material.
How about a round of applause for Ward Silver?
Thank you.
I have to be careful not to lean my head too far to the left or right as I drive home. I'm afraid some of it's going to run out all over my shoulder. But great
Well,
information.
just bond your ears together.
There we go. Absolutely. A little bonding in action.